Okay, so we can go through this together for now. Okay. So this is the diagram that we see, and it's actually having the equation of the curve, which is y is equal to x squared. Okay, and we can see that they are n rectangles. Okay, so each of the rectangle is having the width of like 1 over n there. So we need to look at like the part A here. So by considering the sum of areas of these rectangles, show that the integral of the 0 to 1 for the x squared is less than this expression here. So how are we supposed to get this expression? Few things, okay, that we want to like mention about. Here is the integral. Okay, so the integral here actually represents the area under the curve. Okay, so we can actually say something like, okay, the area under the curve here is less than the area of the rectangles. So that's why we actually get this inequalities here. Okay, so of course, the area of the curve under the curve is actually given by this integral exactly. So we're now looking at the area of the rectangles. So the area of the rectangles that we have here is okay. So what we have in this case is that, okay, for each of the rectangles that they have got the same width, right? So the width there is 1 over n. So we will just like have the 1 over n. Okay, and what we need to multiply to this 1 over n is that we have to look at all the heights of the rectangles. So we just need to get like all the heights of the rectangles. So the heights of the rectangles here are based on the value of the x that we have, because the heights here are all related to the y value. Okay, the y value of the curve. So let's say for the first height that we have here, right, we have got 1 over n. The next is when we have got the x is equals to 2 over n, that gives us those heights there. And at last, okay, when we go to the last value of the x, which is a 1, it gives us the last height. Okay, and how do we get the height? Is we substitute the x equals to 1 over n inside the x squared there, and so on. So these are all our heights there. Okay, so what are we getting next is we are getting all the, we can see there's a 1 over n squared, 2 squared over n squared, and so on. Okay, so how do we actually like change that to like the expression that we see in the question there is actually that we are going to consider the sum, okay, of the squares. But before we can actually do the sum of the squares, right, we have to factorize the denominator out first. So all the denominators has got the n squared. So we factorize the denominator out first. So once we factorize the denominator out, inside the expression there, right, it is just our 1 squared, 2 squared, and so on. So of course, when we factorize the n squared out from the last term, right, it will give us an n squared from there. So it's something that we are quite familiar with that already. Okay, so in the bracket here, it's a sum of the squares from 1 to n. So sum of the squares from 1 to n, we know everywhere is 1 over 6 and n plus 1 to n plus 1. We just have to like tidy up the things from there. So actually get like n plus 1 to n plus 1 over 6n squared. We just have to like expand that. Okay, so with that, we can actually get this the right hand side there already for the inequality. Okay, so like also this kind of the questions, right? We need to also look at like, are we actually looking at the approximation for the area under the curve, or are we looking at the approximation for the rectangles, which is represented by like the series there? So in this case, what are we trying to approximate is we are approximating the area under the curve. So the area under the curve here should remain unchanged. The one that is going to change, or what we want to find for the upper and the lower bound, is the area of the rectangles. So we actually wanted to do something like this here. So we actually prove for this is the upper bound. So we are going to find the lower bound later in the question there. Okay. So usually the question, right, they will give us a curve in order for like to prevent any different way that we are actually looking at the graph and also the rectangle. So they will surely give us the first diagram. So usually the part A will be based on the diagram that they actually gives us here. Okay. So now we look at the second part of the question for this. It's okay. Now we need to use a similar method to find the lower bound for the this integral here. So this integral again is area under the curve. It's not going to change. So when the area under the curve is not going to change, what we're going to change here is the height of the rectangles now. So before this, okay, we want to find an upper bound. Okay, if you look at the part A here, right, we want to find an upper bound of an area. So it means that the rectangles must be larger than the area. Now we want to find a lower bound. Lower bound means the rectangles must be lower or smaller than the curve. So all the rectangles must stay below the curve. So if that is the case, okay, again, we are not changing the area under the curve. That is, we have to change the heights of the rectangles to make them all shorter, okay, or lower than the curve. So the rectangles that we actually have now would have this height for the first one, and then this is our second height, this is our third height, and so on, until the last height that we actually see there, right, is until here only. Okay, so these are the heights that we will have in the this situation. So let's look at the how do we get the areas of this set of the rectangles here. So our lower bound is given by like 1 over n, which is the width of the rectangle, multiplied by, so the same thing, okay? We sum in all the values of the x to get all the heights there. So the first height is actually starting at the x is equals to 0. That gives us the first height there. Next one is a 1 over n and so on. And okay, the last height, okay, the last height is only at the x is equals to x minus 1 over n. Sorry, n minus 1 over n, sorry. Okay, so that is the lower bound, which is the area of the rectangles where we have actually made the rectangle shorter. Okay. So after that, tidy out a little bit. And inside there, we also see there's we can use the same technique or same trick that we have actually done before. We can factorize out the n squared from the bottom. So once we do that, okay, inside there, we only have got all the 1 square, 2 square, and so on until this is like n minus 1 square here. So with this, tidy up a little bit. So this is the sum of the squares again, but we only sum until the n minus 1. So from the formula is 1 over 6, n plus 1, 2n plus 1. Okay, so from here we can tidy the things up. So we get 1 over 6n, okay, multiplied 6n squared, sorry, multiplied by this. We have to expand the n minus 1 and then the 2n minus 1 there. So once we actually expand that, we will actually get a nice expression. Okay, so that's how we look at this the lower bound here. Yeah, so in the question, we just have to be sure, like in the very first step, that are we approximating the series or are we approximating the area under the curve here? Okay, so let's look at the other questions from here. Okay, so this is also some similar tricks that we can actually apply from there. So whereby we see this is like a y is equals to 1 minus x cubed. Okay, from 0 to 1. So we have the set of the n rectangles, which is like the width 1 over n. So by considering the sum of the areas of these rectangles, okay, show that the integral for 1 minus x cubed from 0 to 1 is less than or equals to this right-hand side here. So again, we can see that this is actually for us to approximate the area under the curve, which we have to look at the area of the rectangles. So for the area of the rectangles that we actually see here, right? Okay. So okay, when we look at the area of the rectangles, So how do we get the area of the rectangle here is that, okay, of course we have got all the width there. The width is 1 over n. Let's just put the 1 over n first. So we're using this to multiply all the heights, okay? The heights that we have there is, okay, we see the first height is given by when x is equal to 1 over n. Sorry, 0. 1 over n, 0. So you can see the first height is here. And then the next height is when we have got the x is equal to 1 over n and so on. Until the last height there, we are actually having the x is n minus 1 over n there. So we have to sub all those in, okay, all those x inside the function y there. So for the first y value is 1 minus 0 cube. Let's put a bracket plus 1 minus 1 over n cube plus 1 minus 2 over n cube. Sorry, the cube, I should put it outside there. And then, okay, until the very last one there. So 1 minus n minus 1 over n cubed there. So from here, we need to try to find a way to tidy up, okay, the expression here. So we can actually see that, okay, the thing here, we have got 1 over n. And inside the square bracket, right, because we have got like n values of the x that we have substituted. So we have got like all the ones there, okay? So for all the ones that when we add them together, supposedly it should give us the n. So we get 1 n for that. And after that, we have got all the minus, okay? So it will give us like the minus, and then we have got like 0 cube, 1 over n cube, 2 over n cube, and so on until the n minus 1 over n cube, right? Let me just write the details so we can see clearer. So with this, right, we know that we can actually factorize the n cube out from the denominator. Okay, so inside there, it is just becoming 1 cube, 2 cube, and so on until we got the n minus 1 cube. Okay, so for this, you can actually simplify the things by applying the formula. So you can see this is like a sum of the cubes for the formula there. So we know the formula for this one is 1 over 4. So it's a n minus 1, yeah? So it's n minus 1 squared and then n squared. Okay, the term there is until n minus 1 only. So here we can start to like tidy up a little bit already. So this is 1 over 4n of n minus 1 squared. So, okay, so it depends how you want to tidy that up. So maybe if we actually expand. So for this, we can actually make the same denominator as a 4n squared. So by using like this is 4n squared, sorry, 4n squared minus n minus 1 squared from there. So just tidy that up. Expand and tidy everything up. So with that, we're actually able to get what we want to prove in the question there. Okay, so that's how we find the upper limit, the upper bound here. So we can use a similar question here. Okay, the similar question that we have here, like a similar idea here is actually proof for a lower bound. So again, we want to find a lower bound for this integral. So it means that we want to find something that is less than it. So we want to find what is this one. Okay, so it means that we're using the rectangle to do that. And our rectangles here, okay, must be all smaller than the area under the curve. So if our rectangles looks like the rectangles, okay, which is like smaller than the curve, then our rectangle will become something like this already. Okay, and then until the last rectangle, we'll actually have like the height, which is just right here. Okay, so basically, okay, the area that we're actually looking at for the rectangle here is, okay, still we are using the width multiply by all the heights. Okay, just look at like what is the height for the first one. The height for the first one here is x equals to 1 over n. So this gives the first height of the rectangle. So you sub in the 1 over n to the function y there, and so on. Okay, so what we have in the last one there, the last height here is actually given by the x is equals to a 1. So the method in simplifying is similar to what we have actually done before here. So we have got all the ones there that we can actually add them together to get the n, and then minus. Okay, so inside here we're actually getting 1 over n cubed plus 2 over n cubed and so on until we get like a 1 cube. Okay. So it's the same thing that we actually simplify inside there by considering, okay, this is now we factorize the n cube. So the sum that we have here is the 1 cube, 2 cube until the n cube at the end. Yeah, because the 1 cube at last there, we factorize the n cube out, so it should give us the n cube. Okay. So apply the summation formula. So this is 1 over 4 n squared, n plus 1 squared. So it depends how you want to work on that. So maybe we expand. So this is 1 minus, and we've got 1 over 4 n squared multiplied by this n plus 1 squared here. Okay, so when we combine the two terms together, get 4n squared at the bottom. So this is 4n squared minus n plus 1 squared. Okay, we just expand from there and tidy up. We get 3n squared minus 2n minus 1 over n squared. Okay, this is the thing that we're looking at. Right? Okay. So that is for the second question. So, okay, so you can see that, okay, they are like different questions, okay, that we can actually use a similar way to do it. So the questions that we actually see here are all about like when we have like the curve given, and then they ask us to do something, to prove something like this. So like for this one, it's actually to look at like the integral for the x cube from 0 to 1 is less than this un. Un is given by this expression here. So like how do we actually end up with this kind of the expression here? It's again considering all the heights of the rectangles there. Okay, so for our un here, okay, let's see how do we get the area of the rectangles here. So the area of the rectangles here is that we have got the width, okay, multiply by, so we just have to sub in those heights there. So you can see the first height of the rectangle is when we have got the x is equals to 1 over n. Okay, and then the second height is when x is equals to 2 over n. So we sub that into the y there equals to x cubed there. And then, okay, let's see what is the last height there. The last height there is when we have got the x is equals to 1, which gives us this last height here. Okay, so with that, we have this. Okay, and then we know that, okay, from all the previous trick, we know that we can factorize the n cube out. So when we factorize the n cube, we get n power 4. So inside here, we are only having 1 cube, 2 cube, and so on until we have got an n cube there. So again, which is just the sum of the cubes. So sum of a cube is 1 over 4, n squared, n plus 1 squared from our summation, yeah? So it's very nice. We're actually getting a n plus 1, the whole thing squared, divided by a 4n squared, which we can factorize the squared out. So this is why we're actually getting like our un here. Okay, so usually the things like this is more to look at the summation that we have learned in the FP1. Okay, so similarly, okay, in the second part, use a similar method to find, okay, instead of n, a lower bound. So a lower bound means there must be something that is less than it. We want to find this lower bound here. So if we have the lower bound for this set of the rectangles here, it means that the rectangles has to be smaller or below the curve, okay, because it has to be smaller with the area under the curve. So for now, okay, our rectangles will actually be like at the starting at the 0 here. The next side is when we have got the 1 over n. Next side is the 2 over n and so on until the last side here is just until here only. Okay, so we do the same thing. The lower bound is the width multiplied by all the heights there. So the heights there is starting with like 0 for the x. We've got 0 cubed plus the next height, 1 over n and so on. And until the last height there is only until the n minus 1 over n. So inside the square bracket there, we have got all the cubes there. Then we have got the n cube at the bottom that we can factorize it out. So the outside there becomes like n power 4. Inside the bracket here, we have got like this is all the cubes starting from 1 until the n minus 1. Okay, so again, applying the formula. This is 1 over 4. It's n minus 1 squared and an n squared from there. Okay, so we can cancel off the things. We are getting n minus 1 squared over 4n squared. So if you want to like have a similar form that looks like the upper bound before, we just factorize out the square. Okay, this is the expression for our the lower bound, the Ln there. Okay. So if we continue to look at the other part, so they might be like asking some other additional question from there. So find the least value of the n, okay, such that the un minus ln is less than 10 to the power of negative 3 here. Okay, so we look at the situation here. Okay, we already have got the un and an ln. So the un is this expression. Ln is this expression. Okay, this is our un minus ln. So we might want to simplify a little bit first and we will see. Okay. So how do we simplify is, of course, we could like expand as usual. Okay. So, okay, let's just expand that, okay, to see what happened. So this is we are getting n squared plus 2n plus 1 minus n squared plus 2n minus 1 over 4n squared. So it's good that when we actually like simplify everything from there, right? It is just giving us a 4n at the end there. Okay, so it's just giving us the 4n at the end there. So here is 4n over 4n squared, which is just 1 over n. So if our un minus ln is less than 10 to the power of negative 3, it means that our 1 over n is less than 10 to the power of negative 3. The n is greater than 10 power 3. Okay. So the thing, okay, is also it's not the question here, right? It is not asking us to find something like, say, set of the values of the n. Okay, it actually asks us about the least value of the n. So we need to give like what is that value exactly. So if in this case, our n is like a 10 power 3, so from here, right, we need to really give the least value. So the least value that we could take of the n here, right, is 10 power 3 plus 1. Yeah, because 10 power 3 is 1,000. So n must be greater than 1,000. So the least value of the n that we should take here is 1,001. Okay, or you just write the 1,001. Yeah, so if you don't give this value, you won't get the last part from there, yeah, because they ask for the least value, not the set of the values of the n or range of the values of the n, this kind of thing. Okay. Okay, so let's look at other types of the questions from this. Okay, so you can see this is something similar. Okay, you can use the same technique to prove all these things. Okay, so you can see it's like very similar one, all the things. Okay, so we look at other types of the question. Okay, let's look at this one. So we have got the curve which is 1 over x squared. Okay, together with a set of the n minus 1 rectangles of unit width. So by considering the sum of areas of these rectangles, show that we have got this thing here. Okay, so we see it seems like, okay, we are seeing a summation here already. And we will actually see, okay, what does this summation really mean, okay, by that is we are actually like approximating this summation. So when we are trying to approximate this summation here, the summation here is fixed, okay? So the summation here is fixed in a sense that we are actually trying to look at like the area of the rectangles in this way. Okay, if we look at the this uh, series, right? When we sum in the r equals to 1 until the end there, right? It is going to give us the area of the rectangles, right? So when the r is equals to 1, right? It gives us a 1 over 1 square. So in fact, right, the rectangle for the 1 over 1 square, right, it should be referring to this rectangle here. Okay, it should be referring to this rectangle here. But the thing is, okay, in the diagram, we do not have that rectangle, in fact. Okay, we don't have that rectangle. So what could be the reason? It's because we can't really integrate from the 0. Okay, you see, if we consider the first rectangle here, right, until the last rectangle is here, right? So this set of the rectangles, okay, is actually having the sum which is like, okay. So we see what is the height here. The height is 1 over 1 squared plus 1 over 2 squared and so on, right? Until the 1 over n squared, right? Okay, so this is actually less than the area under the curve from 0 to 1. Sorry, 0 to n, sorry. But when we integrate this later, it is going to give us something that we can't find the value because we will get something like -1 over x. Later, we need to sub in an n and a 0. So we can't do that. So we can't directly compare that. Okay, we can't directly compare that. So what happened here is that we are only going to compare from the first rectangle that we see here. Okay, so from the first rectangle that we see here, the height. Okay, let's look at the height here. The height is given by the x is equals to 2. So in this case, we will have the first height is a 2 until the last height here is n. Okay, when the x is equals to n there. So this is less than, okay. So when we compare this directly, right, we are just comparing from 1 to the n only. Okay, we are just comparing from the 1 to the n only. So we are supposed to integrate 1 to the n of the 1 over x squared. Okay, but it seems like it is not giving us what we wanted to prove from there. So we, so of course the left hand side there is like a 1 over 2 squared. Okay, but when we write it into the summation, okay, it wouldn't start with the 1. We want to get this. Okay, so the method to actually like to deal with that is we can actually add like the term to the left hand side. And also we'll do the same thing to the right hand side there. So the integral is not affected at all. We are able to still find this integral here. So the left hand side here becomes like r equals to 1 to the n of the 1 over r square already is less than 1 plus, so we just integrate this one. Okay, so this is sorry, that one is an x, right? So we get like 2 minus 1 over n. So therefore, we can actually prove that already. Okay, so that's how we can actually look at this thing here. Okay, so in the next part of the question, okay, we will expect already. They will ask us to find the lower bound. Okay, for this we have asked. We are actually like asked to find the upper bound. So we now need to find the lower bound. Okay, so for this lower bound is what? Okay, we are having these rectangles, and the lower bound here is actually like obtained by certain integral. So we are comparing this with the area under the curve. So we must have the area under the curve, which is below the rectangles. Okay, so again, when we actually look at the area of the rectangles here, okay, so for this area of the rectangles here, right, it is like we have got originally all the rectangles are like this. So if we are trying to approximate the series, means the rectangles are not going to change because the rectangles are giving us this series here. So we are not going to change the rectangle, okay, from our usual way of doing it. Later, maybe I'll show you an alternative for that. But yeah, we now going to fix the rectangles. So when we say sort of like we want to fix the rectangles, it is that we need to consider pushing the rectangles. Okay, so the thing is like this, just now we didn't include the first rectangle here, right? Because of the integral, we can't compare that straight away. But in this case, if we consider like having the first rectangle with us from there, and now we push all the rectangle to the right by 1 unit. Okay, if we do that, the rectangles will now become like this already. Okay, so with this set of the rectangles, we are actually getting the series. Okay, we don't need to like what we do just now is okay, we purposely add one more term to make it like the r starts with the 1 here, right? But once we actually consider like the first rectangle that we didn't do, but we push it to the right by 1 unit here, it's complete now already one. So from here you can see okay, I think I just do the working here. So from here you can see that okay, what is the first height of the rectangle? The first height of the rectangle here is x is equals to 1, which gives us a 1 over 1 square already. And the last height of the rectangle here is when x is equals to n. So it will also give us like the 1 over n square at the end. So from here, right, we can already start to write like, okay, the sum of this set of the rectangles, which is what we see in the green here. Okay, so what are we comparing now? We're actually comparing, okay, with the area of the under the curve. So this set of the rectangles, which is this summation here should be greater, okay? It should be greater than the area under the curve. So we see now where are the rectangles? The rectangle is starting from 1 to the n plus 1 now, okay? So it's greater than this. So we just have to like integrate from there accordingly. Yeah, I'm lazy to write all the sums there, yeah, but you know what happened there, lah. Okay. Okay, so this is how we can find our lower bound. Okay, so r equals to 1 to the n. So this is a more this is a more common what is that? A more common method, okay, that you won't get confused when you actually like do two different types of the question. Before this is to approximate the area. So you get like the things is that okay, you have the integral in the middle and you have got all the lower bound and the upper bound. So the lower bound and the upper bound here are actually like the area of the rectangles. So for this kind of the case that we see before, right, is we actually change the height of the rectangles, but we didn't actually push the rectangles to the left or to the right. But whereas for this case, right, you can see that this case here is we have the summation is in the middle, and we are trying to approximate that. So this is actually like the area of the rectangles. So the area of the rectangles are unchanged, means we shouldn't touch the rectangles. So the left and the right hand side here, they are actually like about our integral. Okay. But I mean, for the first one, it's pretty much there already. Okay, the first one here is to change the height of the rectangle, like I said. But for the second one here, right, what we did here was we're actually trying to push the rectangle to the left or to the right. Okay, but in fact, there are alternatives that we could do to this. Okay, so the alternative here is we are not going to push the rectangle, but we change the height of the rectangle instead. Okay, we are going to change the height of the rectangle instead. So let's see, okay, what happened from that. I'll just draw another new graph, so if not, it will be very confusing. So the graph looks like this, right? Okay. So we know that this is actually starting from, they give the figure is from 1 there. In fact, it's like here. So let's say this is 1 lah, this is 2 lah, and so on until let's say this is the end here lah. Before this, right, what is the height of the rectangle? Is this one. Okay. Like that. Okay, so this is what we have for the curve before. But what happened here is that, right, for this kind of the question, we could also change the height of the rectangle as well. So this is different thing. Before this, what we do is like, we assume that we have got the first rectangle here, and then we do the pushing. So the rectangles, right, will actually go up until the n plus 1 here. Another alternative that we could actually do is that, which is also acceptable, yeah, if not, I won't go through with you, is that we are changing the height of the rectangle instead, but we just don't do anything to we don't push the rectangle, but we change the height instead. If we change the height, right, so the rectangles becomes like this already. Okay. If we do this method, it means that the area of the rectangles that we are actually obtaining here, right? Okay. Okay, the area of the rectangles that we're actually obtaining here, right, is that 1 over 1 square plus 1 over 2 square and so on until, okay, the last height is 1 over n minus 1 square. And if you actually compare this, okay, so this is actually what? This is actually like the sum of the r equals to 1 to the n for 1 over n minus 1 for 1 over r squared. It's okay, it doesn't matter. So we can compare that first. So with this set of the rectangles, right, the area that we're actually going to compare, it is just in between the 1 and the n. Okay, the good thing, is greater, sorry. Okay, the good thing about this is that we don't need to do the integration again because we already have this information earlier. So we already integrated from 1 to n, and we know that is this 1 minus n plus 1. Okay, so this is going to be 1 minus 1 over n plus 1, but we are still having this So what to do? Okay, what to do to this? Because we want to supposed to prove for the sum, which is like r until the n, not the n minus 1. So we add the terms to both sides there. So we add 1 over n squared to both sides there. So let's say we simplify this one, we get this is n over n plus 1. But we plus the n squared term. Okay, so the left-hand side will already become the until the n for 1 over r squared. So for this one, we just need to tidy up a little bit from there. So as we actually tidy up a little bit, we might get something which is like this. You can just leave your answer like this because there's no requirement saying that what types of the answer that you need to leave in. So you might actually get the expression which looks like this. Okay, this is another alternative method that is accepted. Okay, so you can see like there are two types okay, in general. Okay, the first type, okay, this one, the first type here, nothing much to play with one. It's just changing the heights of the rectangles. Okay, but for the second type of this thing here, right, we could push the rectangle, or we could actually change the height of the rectangle. Both will be accepted, and see which one you prefer to do. Okay, but personally for myself, I'm trying to like separate in between two cases here. So for the second case that we have here, I prefer the pushing the rectangles one because I don't want to actually have like confusion later. And yeah, so this is the different types of the question that we will see. So this is we are looking at the graph, which is we have got the usual log x graph, okay, and then here they already tells us that okay, we have got like n minus 1 rectangles from there. And the first part is to consider again the sum of like the areas of these rectangles. Okay, show that we have got the log n factorial is greater than this whole thing here. So usually the first diagram that they give us here is where we can just base it on. So I mean, like we just have to start by looking at like we have got the area of the rectangles. Okay, so we have got the area of the rectangles here that we have. Okay, is we just look at what is the value of the x that gives us the first height here. The value of the x is a 2 that gives us the first height, and followed by 3 and so on until we have got the value of the x, which is n, that gives us the last height there. So in order for us to actually find the area of the rectangle, it's basically like we have ln 2 plus ln 3 and so on until the ln n. Okay, so basically this gives us like ln 2 times 3 times so on until the n there. So this is why it's actually giving us ln n factorial. Okay, so that is why we get the left-hand side of the inequality. Okay, so how do we get the right-hand side from there is we are comparing, because we actually have like the area of the rectangles is actually larger than the area under the curve. So for the area under the curve there, we have to integrate. So what is the area under the curve that we're actually comparing here is we're actually comparing from the 1 to the n for the area under the curve. So we integrate that function. So area under the curve is we're integrating from 1 to the n of the ln x. Okay, so when we integrate ln x, okay, we can use the by parts to actually do that. So when we actually integrate this, we are getting an x ln x minus x. We can sub in the values here. So n ln n minus n minus ln 1 plus 1. So at last, it is giving us this kind of the expression. Okay, so of course, when we talk about the greater and the smaller, then right, it's better for us to say that in this case, the area of the rectangle is actually greater than the area under the curve. So from there, we can actually conclude the ln n factorial is greater than this n ln n minus n plus 1. Okay, those are the things that we need to do for the 5 marks here. Okay, so if we look at the next one, right? use a similar method, okay, to find in terms of n and upper bound for the ln n factorial. So it means that we need to have the ln n factorial is less than something. So this is the upper bound that we are trying to find that. So here, okay, we look at what is the ln n factorial again. Ln n factorial is actually coming from the rectangles. Okay, so they're actually coming from our rectangle. So in our case here, the rectangle shouldn't be changed. Okay, they are still same set of the rectangle, but what happened like in the part B here is that we could actually push the rectangle to the right by 1 unit. Okay, so once we actually push the rectangle to the right by 1 unit there, then our rectangles will actually looks like this already. Okay, and then our rectangles here will actually go up until the n plus 1 already. So again, the rectangles, okay, the area is given by ln n factorial. So the ln n factorial is unchanged, but we are comparing this with a different area under the curve already. So the area under the curve that we're actually comparing now is from 2 to the n plus 1. So to find the upper bound here, okay, we need to integrate, okay, from 2 to the n plus 1 of the ln x. Okay, so as usual, we can integrate. So we get x on x minus the x, and then we just sub in the n plus 1 and the 2. Okay, so we can tidy out a little bit for our case here. So we will get this kind of the expression. This is a minus n plus 1 minus 2 dot 2. So this is the upper bound. Okay. I mean, here, right, okay, is a possible upper bound. So what is the alternative that we could actually consider from here? Is that because some people, they don't like to use this kind of the technique which we push the rectangle one. Okay, some people, they will just always keep using the fact that they can always change the height of the rectangle. So if you do the change of the height of the rectangles, right? So okay, I'll erase this, yeah. So if, okay, they are actually changing the heights of the rectangles, so it will be something like this already. Okay, so they are using a different set of the rectangles, which is like they change the rectangle to become something that is like a smaller. Okay, so if I are using this like idea here, right? So let's see, our rectangles, right, will have the starting value of the still, okay, the starting value of the height here is when we have got x is equals to 1, which is a 0, it doesn't really matter. And the second value is a 2 here. Okay, up until, so what is the last value of the x that we have for the height of the rectangle? That is an n minus 1. So when we actually like add up all the area there, right? So that is we get ln 1 plus ln 2, ln 3, and so on until the ln n minus 1. We are just having, this is the ln n minus 1 factorial. Okay, but as we actually compare, right? This set of the rectangles, we are still comparing that with the same area under the curve, because the area under the curve that we are comparing here, it is still going from 1 to n. So the area of the rectangles here, which we have got like ln of the n minus 1 factorial, okay, it will be less than the area under the curve that we have found just now. So the n ln n minus n plus 1. Okay, but what we wanted to prove is we want to prove that we have got something that is like a ln n factorial. So from there, what we do is we just have to add the ln n to both sides of the inequality. So with that, okay, the left-hand side will already become the ln n factorial already. Okay, and then the right-hand side that we have here is we can actually factorize the ln n together. So the term there will become n plus 1 ln n minus n plus 1. Okay, so that is another technique that we could actually use here. Okay, so if we compare lah, right? If we compare two different techniques that we are going to use here lah, The technique that we actually like push the rectangles requires us to find a new area. So we need to do the integration again, sub in the values again. That's the first thing. If we do the second thing, we no need to do we don't need to do the integration again. But most of the time, what we need to do is always like we have to add some extra terms so that only we can get what we wanted to prove from there. So it really depends on us what we want to do. Okay. So okay, we can also look at the other question here first. Okay, let's look at this one first. So this is the okay, consider the sum of the area of these rectangles. Okay, show that we have got this inequality. So you can see this is a summation. Okay, so usually when we see the summation, it means that we are trying to approximate the summation with the areas. So when we look at the summation here, okay, it is starting with like the r is equals to 1. So starting with r equals to 1 means we actually have like the x value here starting with a 1. Okay, but as we actually consider looking at this diagram here, right, we do not have the height of the rectangle where we have the x is equals to 1 in this case here. We do not have this one. So in fact, okay, what we actually consider here is that, let's say we just write out the area of the rectangles first. Okay, so the area of the rectangle, okay, is we are having like the first height is not a 1, yeah. So you can see there's no rectangle there, right? So the rectangle that we have here is starting from the 2. Okay, so when we sub in the when we sub in the 2 from there, we get like 2 over 2 squared minus 1. So just show a bit of the working here by sort of like we substitute the things in. So you can see the last height that we have here is when we have got the n, yeah. In which, okay, this can be written as r equals to 2 to the n of this expression. Okay, and then now what are we comparing with is the area under the curve. So because we are actually only comparing from here, yeah, so the area under the curve is starting from 1 to the n in this case. So we integrate that function from the 1 to n. Okay, so the area under the curve that we have here is to integrate from 1 to the n of x over 2x squared minus 1 dx there. In which we are getting 1 over 4 ln of the 2x squared minus 1. And we can actually sub in the n and the 1 there. Okay, which will get like 1 over 4 ln of the 2n squared minus 1. Yeah, when we sub in the x equals 1, it gives us a ln 1, which is a 0 there. So we can now like do the comparison already, because what we actually know from here is that, okay, this sum, where the r starts from 2 to the n here, so we are just using whatever that we have for now first. So this is actually less than, okay, 1 over 4 ln 2n squared minus 1. But this is not what we're supposed to prove, okay? The sum there or the series there, supposedly it should start with the r is equals to 1. So from there, we just add the term from there. The right-hand side, we do the same thing. We also add the term there. Okay, we add the term where the x is equals to 1. Okay, so just add this 1 over 2 times 1 squared minus 1 to the both sides there. Then the left-hand side, we can actually have the sum or the series that starts with the 1 already. And the right-hand side, when we evaluate it, so that's why we see like an extra 1 there. Okay, in what we actually wanted to prove in this case here. Okay, so yeah, this is how we prove or find the first part from there. Okay. So okay, in the second part, use a similar method, okay, to find in terms of n a lower bound for this sum. Okay, again, there are different ways that we could do it. So one way is to consider pushing the rectangles. Okay, so when we push the rectangle, we are going to consider the rectangle that we didn't consider just now for the first one there, from 0 to 1, this one. When we're actually trying to push all the rectangles, right? So it will be here already. So the rectangle looks like this. And then the last rectangle that we see here is like until the n+1. Okay. So when we consider this one, that is nothing much, okay, because if the first height of the rectangle is when we have got the x is equals to 1 already, then it will give us this sum straight away already. Okay, so you can see from there like the area of the rectangles are already in this form. Okay, but you need to find out what is the area under the curve. Okay, so the area under the curve that we have here is we have to integrate from 1 to the n+1 in this case, because our rectangle starts with the x equals to 1, and it actually ends at the x is equals to n+1 there. So we integrate from 1 to the n+1. So again, we have, this is a 1/4 ln of a 2x squared minus 1. So this is 1/4 ln of the 2n+1 squared minus 1. So this is a lower bound, yeah. So lower bound means we will have the area of the rectangles. Yeah, lower bound. Wait. Yeah, lower bound. So lower bound means, yeah. So we have got this area. Okay, so you can see the area under the curve is actually less than the summation, or the area of the rectangles there. Okay, one way that we could do it. So the other way, okay, that we do it is we are not going to push the rectangles, but rather we would just change the height of the rectangles there. Okay, so as we change the height of the rectangles there, right? So the rectangles here will become something like this already. Okay. So if we change the height of the rectangles here, so what happened to the area of the rectangles is it will start with the 1, but the last height is only obtained when we have got the n-1. Okay. So the area of the rectangles that we have here is become r equals to 1 to the n-1 of this sum here. Okay. And when we actually compare this with the area under the curve, so this whole thing, okay, so wait, this whole thing here is actually greater than, okay, it's actually greater than the area under the curve. So the area under the curve that we actually have found just now is actually from like 1 to the n. Okay, so from 1 to the n, the area under the curve is given by this thing here. So we have got, this is 1/4, 2 n squared minus ln, sorry. Okay, but there's still one thing missing there, which is the nth term. So for the nth term, we need to add the nth term to both sides. Just add the n terms to the both sides there. Okay, so we can actually conclude already here. So this is from 1 to the n for the sum r over 2r squared minus 1. And the right hand side, nothing much to change. Okay, so nothing that we can combine. So we just leave it like that. Okay, so again, different ways that we can actually look at it. So it depends, okay, which way that you prefer. Okay, so let's look at the next one. Okay, yeah. So this is the diagram given for x is greater or equals to 2. Okay, and then we have got the number of rectangles that we have here is the n-2 rectangles. So by considering the sum of these rectangles, show that, okay, we have got something like this. Okay, so why is it we have got something like that there? That is, okay, now if you look at the area of the rectangles first. So the area of the rectangles that we have here, right? Okay, the first height is starting at the 3, x is equals to 3. So it means that it is giving us like ln 3 over 3 cube plus a ln 4 over 4 cube for the height of the rectangles until the last height here is for the end. Okay, so here we didn't really care about the width because the width is a 1. So you can see like the width here is usually like a 1 here, one. So we don't have to multiply by the width. I mean, the width is a 1 itself. So it's the same thing. So the area of the rectangles that we're considering here is only starting from the r is equals to 3 for the sum to the end of ln r or r squared. Okay, so what are we going to consider later on is that for whatever that we have here, okay, we are just comparing from here to here. So we are considering to integrate this from 2 to n. So the area under the curve that we have here is from 2 to n. So integrate from 2 to n of the ln x over x squared dx. So why does it have like these like many marks, like 7 marks here, is because we can actually integrate a bit by using like say by parts. Okay, we need to use by parts to actually integrate that. So if we let the u to be ln x and then the dv dx here to be the 1 over x squared. Okay, so du dx is a 1 over x, the v here is a negative 1 over x then. So for this, when we integrate this expression here, it is uv, okay, minus v du dx. So for this, we can actually sub in. So we get like 1 over 2 ln 2 minus 1 over n ln n. So we need to integrate this one to get like negative 1 over x n and 2. So just sub in everything. So that's why it gives us like 7 marks here. Okay, so these are the expressions that we are actually getting. So later we might need to tidy that up. Okay, we are not sure yet, but let's see. Okay, what happened from there. Right. So after that, okay, we also have something that we need to do, which is like we now start comparing for whatever that we have here. So we are comparing the series, which is rectangles. So we see in this case, right, the rectangle is actually less than the area under the curve. So this is less than the area under the curve that we have just found there. Okay. And then in order for us to actually have like the thing which is proven, we need to have the r which starts with a 1. So in order for the r which starts with the 1 there, we need to add the suitable terms to the both sides there. So this is actually accounting for the r equals to 1 to the 2. So right hand side, we do the same thing as well. So when we actually consider the terms, right, it's ln 1 over 1 squared, okay, no space, plus ln 2 over a 2 squared. So the left hand side will become the summation already. The summation r equals to 1 to the n, okay? Yeah, this is r, sorry. So ln r over r squared less than. So a bit of the value that we need to evaluate from here. So we have half ln 2. And then, okay, the last two terms are ln 1 is a 0, so nothing there already. And also like we are having the last term here is 1 over 2 squared with a ln 2, so it's 1 over 4. Okay, and the rest of it, we see what the questions there is giving us. So it's actually quite nice that we can actually minus. Okay, we factorize a minus there. So we get this is like a 1 plus ln n over n. So it's to tidy up the first part there, basically. Okay, so the first part here, they have something like 2 plus 3 ln 2. So basically, it's actually factorize the 1 over 4 up. Okay. So, wait. Actually miss out the half there, right? Yeah. So yeah, when we actually tidy up, we are actually able to get the expressions there already. So this is 3 over 4 ln 2. So 2 plus 3 ln 2 over 4 minus this whole thing. Where? No, it's just an n. Let me just check. Okay, yeah, so this is the expression, okay, at the end. Okay. So with this, okay, we're going to look at the another part here. So again, it's a similar thing that they actually ask us to find a lower bound. Lower bound means we need to have something which is less than this. Okay, so or it actually means that the area under the curve should be smaller than this, which is the area of the rectangles. So from there, right? Okay, they are quite. I mean, there are quite a few ways to actually do it. There are different consideration that we could do. Okay, let's say now we consider doing like the pushing the rectangles. Okay, so as we push the rectangle, right, it is possible for us to assume that we have got this rectangle here, and then we are going to push it to the right. So when we push all the rectangles to the right, okay, the rectangles that we're actually having here is here, here, and so on until the last rectangle here is up until n+1. So we're actually going to now integrate, okay, this from 2 to the n+1 for the area under the curve. Okay, it's to integrate from 2 to n+1 for the function. So, yes. Okay, so the after that, okay, what we have is we just look at whatever that we have actually integrated earlier. So this is the thing that we have actually integrated earlier, right? But it is actually in terms of the n. But now we have got the n+1. So basically, the expression there would just be the same. Just that all the n's there, we change it to the n+1 only. Okay. But still, when we actually have the area of like these rectangles, right? So the rectangles here is actually now starting from the 2 already. Okay, and the last height of the rectangle here is when the x is equals to n. So when we consider the area of the rectangles here, it is actually that we have got the sum of r equals to 2 to the n from the this ln r over r squared. Okay, because the first value is starting from the 2, yeah. So we sub into this one here, then it will give us the r is equals to 2 here, which is the same as the sum of r equals to 1 to the n. Because ln 1 actually gives us a 0, so we can just replace like the ln 1 term like with the r is equals to 1 there. So we can start with the r is equals to 1. Basically, it just gives us a 0. It's the same thing. For this, we can just straight away compare already. So the area under the curve is actually less than the area of this rectangle here. So in other words, we have this area under the curve. All kind of the expression there. If you want to combine that, it's up to you. But if you don't want to combine, it's fine. It's less than this summation here. Okay, so that's how we look at it. Other method, other way is to considering doing a different set of the rectangles. So if we do a different set of the rectangles, we now change the height of the rectangles. We make all the rectangles higher. Okay, so as we make all the rectangles higher there, so we can actually say that here, the area of the rectangles, right? When we look at the values of the x, from there, the first height is given by 2, the last side is given by n minus 1. So it's actually r from the 2 to the n minus 1 of the sum here. But this is good, okay? When we actually compare this area, okay, when we compare this area with the area under the curve, right? So we are still using the same area under the curve because the area under the curve here is from 2 to the n here. So what we could do is the area under the curve is just what we have actually found earlier in this part here. So just use back, okay, this part of the area under the curve here. Okay, so you can actually use this. Okay. So, okay, what we need to do, okay, for the next one is just like, we need to actually just complete the sum there. So the sum is actually going from 2 to the n minus 1. It's the same as we are going from like 1 to the n minus 1, but we just have to add the extra term there, which we have to add the ln n over n squared term for the both sides. Okay, for the both sides there, then the left-hand side is already the sum from r equals to 1 to the n already. So the right-hand side is this whole thing here. See whether you want to like tidy that up. If you don't want to tidy that up, it's really up to you. Okay. Okay, so you can see two different types of the questions about like doing this series here. Okay. Okay, so there's another type. There's another type of the question, which is something like this here. So we so it looks like a question that is like we want to like do all the approximation, right? But we can actually look at like this is a curve. Okay, it looks a bit scary at first, and they actually ask us to show that okay the sum of this I equals 1 to n of this function here is actually less than the ln like so many things here. So in fact, what really happens here is that we have got the things which is like okay. Let's say if you look at the area of the rectangles, right? The area of the rectangles here is really given by this summation already, because the first height is x is equals to 1. The last height for the rectangles here will be x is equals to n. So it really like is given by this sum already. Okay, so now we compare with the area under the curve. So area under the curve here is we got to integrate. Okay, so let's look at what is the area under the curve. The area under the curve here is from 0 to n, right? From 0 to n there. So we need to integrate it. So we need to, so this question is actually testing us on how to integrate this rather than they ask all the upper and the lower boundary stuff there. Okay, so there's quite a bit of work for us to actually do here. Okay, if you want to do the integration here, that is, we need to complete the square first. Okay, or else it's very difficult for us to integrate. So when we complete the square, is x plus half squared, and then we are getting plus 3 over 4. It's an n, sorry. Okay, so if we recall, okay, what is the form for this one? Is like we are integrating the form which is like 1 over square root of the x squared plus a squared form. So we know that when we actually integrate this one here, it is giving us like arcshine of the x over a. Okay, it's the arcshine of the x over a. From here, we will actually get arcshine of the x, okay, this is our x, over the a here is a set 3 over 2, yeah? Because the 3 over 4 is the a squared itself, the a is a set 3 over 2. And we are supposed to like evaluate it at n and also the 0. So tidy up a little bit first for the arcshine first. Inside there is a bit ugly there. So okay, let's see what is the form that they want. Okay, they have something like that there. So if we try to evaluate this a little bit, okay, for the x plus half over a set 3 over 2 there, we can actually like multiply instead. So we can multiply by 2 over set 3. So still the 2 over set 3 is not a nice value because we have got the denominator at the bottom here. We rationalize it. Okay, so this is the expression of the arcshine. So the arcshine that we have here is set 3, sorry. Okay, so if we actually do this, we are actually multiplying by 2 set 3 over 3 for this expression here. So there are too many brackets there because we just want to get a nice expression from there. So this is a 2 set 3 over 3x plus this is a set 3 over 3 with the n and the 0. Okay, so when we actually sub in the n and the 0 there, so we are getting arcshine of the 2 set 3 over 3 n plus set 3 over 3 minus arcshine of the set 3 over 3. So from there, okay, what we got to do is we got to actually use the ln form of this arcshine. Okay, so the ln form of this arcshine is a ln. So you look at the formula booklet, the ln form of this one is ln of the x. Let me just check. I forgot that it's a plus or minus. Just let me check the MF90 for a while. Wait. Plus. So it's so the form is okay. I write you the formula here. Arcshine of the x is ln of the x plus x squared plus 1 like that. Okay. So for this, okay, for this form here, then we are actually getting the ln. Okay, so this is ln, and then this whole thing. So 2 over 3 x plus this 3 over 3. Okay. Plus with the square root of this whole thing squared. Plus a 1. Okay, minus. This is also an arcshine, but it becomes something that is easier already. Plus, so this is a square root of the 3 over 3 squared plus a 1. So it's actually quite a bit of the thing that we have to do from here, lor. So inside the square root together with the plus 1 and the square thingy there, right? So we're actually getting this is a 4 times 3 over 9. So it's 4 over 3. So 4 over 3 x squared plus, so this is 4 over 3 x plus, I guess it's a 4 over 3 as well. Let me actually expand everything there. And then this is a minus ln set 3 over 3 plus, this is 4 over 3, set of a 4 over 3. So we'll actually like open up everything from there, right? So this is ln of the 2 set 3 over 3 x plus set 3 over 3 plus, so when we factorize the 4 over 3 out, we get 2 over set 3, okay, of like this whole thing, x squared plus x plus a 1 minus the ln of, so for this one, we're actually getting set 3 over 3 plus a 2 over set 3 there. So we can actually like try to tidy up the stuff, yeah, because what we want at the end here is we are getting just some expression which looks like this here. So basically, okay, what we got to do is we just have to multiply this whole thing. So it's a simplifying process that is actually a bit painful there, but otherwise it should be quite okay one, right? Okay, the long term that we have, right, for the last long term here, we can actually combine them. So as we actually combine them, we actually get like, okay, let's just do it at the side here. So cert 3 over 3, so plus this is a 2 cert 3 over 3. Okay, which is we get 3 cert 3 over 3, which is just a cert 3 itself. Okay, so it is to have like the ln of this is just a cert 3. Hey, sorry. So cert 3, okay, that we have there means we have to divide the first term here, everything by the cert 3 because we're actually combining the ln there. So finally, this is what we get. Okay, so you can see everything there like 2 over 3x plus 1 over 3. Okay, and also like the 2 over 3. Hey, it's n, yeah. I'm actually doing all the x here, but it should be n here, yeah. I keep doing all the x there, but all the things there are actually n lah. So it's a simplifying part that makes it a bit like very headache only. Okay, other than that should be okay one.